Welcome to my video course on engineering FRMCS. Today, we're exploring one of the absolutely most vital foundational pillars of the future rail mobile communication system: quality of service and the prioritization framework. When we're dealing with high-speed trains moving across massive digital networks, ensuring the exact right data gets to the exact right place at the precise millisecond, well, that isn't just a matter of network efficiency, it's literally a matter of absolute safety. So we're going to look really closely at how abstract application requirements are mapped all the way down to physical transport flows. Let's dive in.
Here is our structural breakdown for today. We've got 1. Introduction to FRMCS QoS. 2. ETE application KPIs. 3. The prioritization framework. 4. QoS Mapping Architecture. And finally, 5. Transport-level resource flows.
All right, let's kick things off with Section 1, Introduction to FRMCQoS.
We'll start by examining the fundamental architecture that actually makes all this mission-critical railway communication possible. In a modern railway system, communication isn't just some giant monolithic pipe of data. It's incredibly structured. Notice the clear separation of responsibilities we have here. As we peel back the layers of this system, try to keep this visual map in the back of your mind. We're drilling down from the red application stratum at the very top, moving through the blue service stratum in the middle, and eventually hitting the gray transport stratum at the base. Now, the application stratum is where the actual railway operations live, right? And the transport stratum provides the raw connectivity based on 5G specs. But that middle layer, the service stratum, that's our crucial bridge. It handles session management, group communications, and most importantly, it interprets what the applications need and tells the transport layer exactly how to deliver it.
Moving right along to Section 2, E2E Application KPIs.
So at the very top layer, the entire system's requirements are driven by end-to-end key performance indicators, or KPIs. Think about it. When a train is barreling down the tracks at 300 kilometers per hour, milliseconds genuinely matter. So an ETE KPI guarantees that the data journey from, say, a train's onboard system to the trackside control center meets absolute, uncompromising performance standards before it even leaves the station. It is the strict, non-negotiable network performance requirement measured precisely from a transmitting source application to a receiving destination application right at those system boundaries.
And looking at this breakdown really brilliantly illustrates why a uniform, one-size-fits-all network approach simply doesn't work for railways. Notice the stark contrast in demands. The European Train Control System, or ETCS, requires near-instant, ultra-reliable delivery. Why? Because this is the data that literally stops trains from colliding. Automated train operation also demands very low latency and ultra-high reliability. But on the flip side, something like onboard video surveillance, while obviously still important, can totally tolerate moderate latency. It just doesn't need those same microscopic time guarantees.
Which brings us to Section 3, the prioritization framework.
So the huge engineering question becomes, what happens when network resources get congested and multiple applications demand access all at the exact same time? Well, to prevent total systemic failure during a bottleneck, the network enforces a totally rigid prioritization framework. If the available radio resources just aren't enough to handle the overall demands, the FRMCS system utilizes strict priorities to give preference to those higher priority applications. Every single communication session can have its own individual parameters, completely independent of the others. And hey, if the system goes temporarily blind and can't associate specific QoS requirements with a session, it's smart enough to just apply a predefined default. This ensures that our mission-critical communications will always, without fail, override the less important traffic.
Honestly, just think of this framework like a massive digital highway with highly regulated traffic lanes. Life-saving data like an emergency braking command from the ETCS gets instantly routed into an exclusive VIP fast-track lane. Nothing gets in its way. Meanwhile, standard onboard video surveillance feeds just keep cruising along in the regular traffic lanes. They'll still get to their destination, sure, but they have to yield to the emergency traffic whenever the network gets crowded.
Next up, Section 4, QoS Mapping Architecture. Let's descend into that middle service stratum to observe how these high-level priorities are actually converted structurally into real network instructions. This critical conversion is fundamentally a three-step process. First, the application function maps the session description information. Basically, it takes what the application is asking for and formats it. Second, this service information is securely passed over to the policy control function, or PCF, which basically acts as the network's brain for rules and policies.
Finally, the PCF requests and authorizes the specific 3GPP quality of service parameters needed to lock down those resources across the whole network.
This mapping process is that vital mediator layer we talked about earlier. It seamlessly translates abstract human-readable KPIs, like, say, I need ultra-high reliability, into the numerical 3GPP parameters that the 5G network core can actually understand and execute. Specifically, it assigns values like 5QI, which is the 5G QoS identifier, and ARP, the allocation and retention priority. These mathematical parameters are what tell the transport layer exactly how to treat every single packet of data flowing through it. It's how we guarantee our VIP traffic actually gets its fast-track pass.
Finally, we hit Section 5, Transport-Level Resource Flows.
Drilling all the way down into the transport stratum, this is where the math dictates the physical data movement. Down here at the foundational level, the 5G network strictly enforces the converted rules by applying QoS directly via PDU sessions. Get this, a single piece of user equipment, like a train's onboard radio module, can handle up to 15 parallel PDU sessions. And within each of those sessions, resources are divided even further into up to 63 highly specific QoS flows. IP data packets are meticulously mapped and filtered into their corresponding flows based on all those rules we just discussed. And this strict enforcement doesn't just happen in one spot. It happens simultaneously at the user equipment, at the trackside radio base station, known as the G-Node-B, and deep inside the network core at the user plane function.
Taking a look at the data paths carved out by the user plane function, or UPF, you can really see how this works in practice. Whether the train is rapidly moving between cells or needs some really complex multipath connectivity, the UPF ensures the data flow always follows those strict QoS policies established by the PCF. It actually modifies the data path on the fly to guarantee that the application's KPI is delivered without fail, maintaining an unbroken chain of priority all the way from the software application down to the physical radio waves.
So, bringing it all together, how does a modern digital railway truly guarantee safety? It does it by flawlessly, continuously converting those abstract application needs into highly regulated, strictly prioritized physical transport flows. By mastering this complex translation from end-to-end KPIs all the way down to 5G QoS flows, FRMCS ensures that the most critical data always has the right of way. Thanks, we can see you next video.